Okay, so we're living in this age of absolutely incredible AI, right? We've got models that can write poetry, spit out code, and answer pretty much any question we throw at them. But, and this is a big but, even the most powerful of these systems has this fundamental, almost hidden limitation, a problem that really keeps them from truly learning the way you and I do. I want you to think about it like this. What if these brilliant AIs are just stuck in a perpetual present? They're unable to form new long-term memories from their experiences, kind of like someone with anterograde amnesia. They can process what's right in front of them, sure, but once that conversation's over, that new knowledge just poof, fades away. So today, we're going to dive into a really fascinating new paper from Google Research that tackles this exact problem. First, we'll unpack AI's memory issue. Then, we'll look to the human brain for a little inspiration. From there, we'll introduce this new idea called nested learning, which kind of forces us to rethink how AI learns at a really fundamental level. And finally, we'll meet Hope, a brand new model that puts all this theory into practice. Let's get right into it. All right, first up, let's get to the very heart of AI's memory problem. The paper calls it the anterograde amnesia of LLMs. And honestly, it's the perfect analogy for why these models, for all their power, are basically static. This slide really just lays it all out, doesn't it? On the left, you've got our current AI models. They're essentially frozen in time after their training is done. Their knowledge is locked in. But then you look over on the right and you have the human brain, a system that's literally defined by neuroplasticity. It's constantly changing, constantly forming new, permanent memories from everyday life. It's a night and day difference. And this quote from the paper just nails it. The AI's knowledge is split between two extremes: the immediate present, whatever fits in its context window, and the distant past of its pre-training data. There's no bridge between the two. New information can't be consolidated into permanent skills or knowledge without starting that incredibly expensive training process all over again. So, if the current AI design is the problem, where do we even start to look for a solution? Well, as it so often happens, we can look to the most efficient learning machine we know of, the human brain. It really does provide the perfect blueprint. You see, our brains use this really cool two-stage process to make memories stick. First, there's a super fast online consolidation that happens right after we learn something new. It just stabilizes the information. Then there's a much slower offline process, which often happens when we sleep, that reorganizes and strengthens those memories for the long haul. And the researchers here, they really focused on that first, rapid online process as the key inspiration for a new kind of AI. And this brings us to the core idea of the paper. It's a whole new paradigm they call nested learning. And to get it, we have to move beyond this sort of flat, one-dimensional view of how artificial intelligence actually works. But first, we need to get our heads around a crucial distinction here, one that's borrowed straight from neuropsychology. Memory is just the raw update that happens when the network sees a new input. But learning, that's the process of making those memories effective and useful. It's about storing information in a way that actually improves the whole system. What this means is that current AIs are great at short-term memorization, but they're not so good at true learning. So, nested learning proposes this pretty radical shift in perspective. Instead of seeing an AI model as one giant single process where everything updates at the exact same time, we should think of it as a system of nested processes. You can almost picture a set of gears turning at different speeds. Some are spinning really fast, reacting to immediate info. Others are turning much more slowly, deliberately consolidating knowledge over time. Okay, on to section 4, rethinking how AI learns. This new nested perspective really forces us to reconsider what's actually going on during AI training. And when we do that, it reveals something the paper calls the illusion of deep learning. The textbook view of AI training, the one we're all used to, is a pretty simple one-level loop, right? You show the model some data, you see how wrong its guess is, and then you just nudge all its parameters a tiny bit in the right direction. And you just repeat this billions of times. It's a flat, single-speed process. But here's the big aha moment. The paper reveals that even with a common technique, like SGD with momentum, we've actually been using a two-level system this whole time without even realizing it. There's a fast inner loop where this momentum thing acts as a short-term memory, keeping track of recent mistakes. And then there's a slower outer loop where the model's main weights are updated based on the information stored in that little momentum memory. So what does this all really mean? It means that the optimizers we use to train models, tools like Atom or SGD with momentum, they aren't just dumb mathematical wrenches we use. They're in fact simple learning systems all on their own. They're acting like memory modules, learning how to compress the history of errors to guide the main model more effectively. They are, quite literally, learning how to learn. Now, this whole insight is way more than just a cool theory. It actually opens the door to designing entirely new types of AI models. And that brings us to our final section, where this idea gets put into practice with a new architecture called HOPE. HOPE, which, by the way, is a fantastic name, is a model built from the ground up on this principle of nested learning. It has something they call a continuum memory system. All this really means is that different parts of the model are designed to update at different speeds, creating this whole hierarchy of learning from super fast to super slow. It's meant to mimic the different rhythms of the brain. Let's just look at this comparison for a second. A standard transformer, the architecture behind models like GPT, is like one single massive gear. Every single part turns at the exact same speed during training. The HOPE architecture, though, it's more like a complex clockwork mechanism. It's got all these nested gears, and each one is spinning at its own rate. This allows for a much more dynamic and multi-layered learning process. And get this isn't just some small-scale proof-of-concept thing. The researchers actually built and tested a 1.3 billion parameter version of HOPE, and he put it head-to-head with a highly optimized transformer baseline of the exact same size. And you know what? The results, they really speak for themselves. On standard language modeling tasks, where a lower perplexity score is better, it just means the model's less confused. HOPE significantly outperforms the baseline. I mean, just look at that language model benchmark score, 11.63 compared to 18.32. That is a massive improvement. And then on the bull queue reasoning task, it scores over 4 percentage points higher in accuracy. This shows that the new architecture isn't just different, it's a lot more effective. So what's the big takeaway here? Well, nested learning gives us a completely new way of understanding and building AI. It's not just a flat process, it's a multi-level one. And this provides a real, concrete path toward models that can actually learn from new experiences without needing to be completely retrained from scratch. And maybe most importantly, it shows us a new way to make AI better that isn't just about throwing more data and more computers at the problem. It's about making them fundamentally smarter. This research really pushes us to ask a profound question. For years, we've been building AI that knows a vast amount of information, but this work points toward a future where we build AI that truly learns. So what new capabilities, what new possibilities are going to emerge when our creations can finally escape the prison of the present and start building a lifetime of their own memories?